Welcome back. After having the mathematical foundation of Laplace transform, we can finally motivate and use transfer function, the relationship between output and input in the Laplace space. By having transfer functions, we can predict how output can change upon changes in input. Before we dive into motivating the transfer function, I want to take a step back and show that there's a difference between using the original variables in the physical space and the deviation variable in the deviation space that we will define later. Here, let's us first find out the Laplace transform output using original variable. So here I have a governing ordinary differential equation, y, the derivative of y with respect to t equals to x minus y, where x is the input and y is the output. And we want to find the Laplace transform output. To do that, we take the Laplace transform of the ordinary differential equation on the both sides, and on the left we have the derivative. We have s of big Y of s minus the initial condition equals to the Laplace transform of small x is big X s minus big Y of s, where we define big X as the Laplace transform of small x, and big Y of s goes to the Laplace transform of small y. And then we separate the big Y and s. So we have moving the big Y to the left and moving the initial condition to. Finally, we can solve for s. Condition divided by s plus 1. This is not so desirable even in this simple condition, in a simple example, because on the right we have the initial condition of y of 0, which is often non-zero in the physical space. And then we also have x of s that is not separable. We cannot write it in terms of the ratio between y of s, x of s. There is no such ratio relationship in the original variable space. And that is why we want to use deviation variables. Deviation variables are defined as follows. Deviation variable is termed y prime, which is a little bit annoying because it conflicts with the derivative symbol, but now we'll just resort y of 1 as derivative dy dx, write it explicitly. And y is the variable in the physical space, and y bar is called the nominal steady state value. So normally what that value is called the nominal steady state value. For example, if I have a heater and want it to be at a nominal steady state of 70 degrees Fahrenheit, and currently the physical temperature in the room is 72 degrees Fahrenheit, then the deviation is 72 minus 70 plus 2. And why do we want to use it? And I will demonstrate now the advantage of using deviation variable by solving the exact same ODE using output deviation. Similarly, we first derive we're given the governing ordinary differential equation. The variables, the x is the input cause and y is the output effect. We want to first define the steady state expression from this ODE. So at steady state, all time dependence goes to 0, and therefore dy dt equals to 0. So we have 0 equals to x minus 1. And because it is a steady state, all variables will be at nominal steady state values. So we will have x bar and y bar. Then we can derive the ordinary differential equation in deviation variable by subtracting these two equations. So dy dx, dy dt minus 0 equals to x minus x bar minus y minus minus is plus bar. To rearrange that, minus y minus bar. And x minus x bar is the deviation x prime, and then y minus y bar is deviation prime. But here we still haven't figured out the derivative. What do we do about the derivative? We can use the derivative of y prime, the deviation variable, t. We know that the definition of deviation variable, and we can plug that in, d dt of y minus y bar. The y is a variable, and the nominal steady state is a constant. So that is just dy t minus 0. So the derivative of the deviation variable is the same as the derivative of the original value. So you can further write that as dy prime dt equals to x prime minus y prime. This is the deviation variable. Note that it looks similar to the original ODE. So you write it out. They look very similar. It's just a prime away, each variable. But you cannot translate them directly. You have to derive them. Because if you have a variable that is held constant, then it will be cancelled out during the derivation. You always have to do such derivation and cannot just simply add primes, and that will cause troubles. You might think that the form that we got for deviation variable is very similar to the original. This is very different. We now want to look at the Laplace transform output deviation. Take the Laplace transform of the ODE of both sides, and we have on the left hand side the derivative s of y prime of s minus y prime of 0 equals to big X prime of s minus big Y prime. And note that the initial condition for the deviation variable is defined as y of 0 minus nominal steady state, a constant. And normally, the initial condition would be at nominal steady state. That is, y of 0 equals to y bar. If we plug it in, this gives us that y prime of 0 is 0. So the deviation is 0. There is no deviation. If there is no deviation, this term cancels out, goes to 0. So rearrange this, make y on the left, x on the right. We can solve for y prime. And notice this time there's no initial condition on the right side, and x prime of s can be separated. What do I mean by separate? We can actually write y and x as a ratio. So if we divide it by both sides by y, I have x prime divided by y of x and then multiply each side by s plus 1. Or we can write it in the reverse. So if I inverse it, we have y prime of s divided by x prime of s equals to 1 divided by s plus 1. And this is way better than before because it gives us an expression scales between input and output. There is a very straightforward input and output relationship. Now is the best time to motivate the use of transfer function and define transfer function. We first define transfer function as it characterizes dynamic relationship of input and output variables in the Laplace space, so the S space. The transfer function is denoted by g of s, and it equals to the Laplace transform of the output divided by the Laplace transform. So in the original variables, we have big Y of s is the output, big X of s is the input. This is original coordinate source. And they are not equal to each other, so but conceptually, in the deviation space, we have y prime of s divided by x prime of s. These are all transfer functions. These are examples. Transfer function, not equal. And again, we define the deviation variable as the deviation from nominal steady state, where we have y prime is the deviation equals to the y value that depends on t minus y bar, which is nominal steady state. We use the deviation variable because it has a vanishing initial condition at steady state. So steady state is very important because steady state means that the initial condition equals to nominal steady state value. And therefore, y prime equals to y bar minus y bar, which is 0. It has a vanishing initial condition. And what we wrote out in the last slide is that y prime of s divided by x prime of s equals to, let's check, 1 divided by s plus 1. And this is the transfer function for that ordinary differential equation. So we have transformed that ODE into a transfer function that describes the relationship between the input and output in the Laplace space. Recall before that we have a difficult ODE to solve, and to go from ODE to its solution. And we take the Laplace transform of ODE that we give it into the Laplace space, to an algebra equation. And then we can easily solve that algebraic equation. In this case, we use the transfer function to describe it. And we can find the solution to the algebraic equation. And then inverse Laplace to solve the hard to find solution for the ordinary differential. Transfer functions can also be used in the Laplace transform for multivariable ODE. In this case, I have a multivariable ODE with x and y as input and z as the output, where dz dt equals to x minus y minus z. And we want to find a Laplace transformed output deviation, z prime of s. So let's still use the deviation variable because we want the output deviation. So first step, we look at steady state condition. So d dt equals to 0, meaning that 0 equals to x minus y minus z. But note that because they're at steady state, they all are in nominal steady state values. So we add bars to all the inputs and outputs. Bars in output. In the second step, divide the original function and the steady state function, and we will get the deviation. Original ODE state and original divided by steady state is deviation. dz dt equals to x minus x bar minus y bar minus z minus z bar. Then we use the definition for deviation variable. We have dz dt equals x prime minus y prime minus z prime. And here prime represents deviation. And then again, for the derivative, we can use dz prime dt, and then use the definition for z prime, which is the original z with respect to t minus z bar, a constant, so that we only have dz equal to each other. So we have dz prime dt equals to x prime minus y prime minus z prime. Here we have gotten the deviation ODE. Second step is deviation ODE. The third step is to get the output deviation by finding the Laplace transform, the ODE both sides. We have S of big Z S minus Z prime's initial condition equals to big X, big Y minus big Z. And we note that we use the vanishing initial condition Z prime of 0 equals to 0, because initially it would be at steady state. Reorganize, we have big Z of S equals to x prime minus y prime divided by s plus 1. This can be further written as x prime divided by s plus 1 minus y prime divided by s plus 1. And this is our final result. And this result is very interesting because if we can hold one variable constant, so if hold, say, y constant, small y constant, then its not deviation will be 0. So therefore, y prime of s will be 0. And if that's the case, we will have big Z equals to x prime s plus t, and we can isolate the effect x as 1 minus s plus 1. And similarly, we can isolate the effect of y. But by having transfer function for multivariable ODEs, we can isolate the effect of each individual inputs and see how each individual input can impact output. This will also come back as we discuss the addition property for transfer function later. Now we know how to determine transfer functions from differential equations, whether it's from the original variable or the preferred deviation variable. Now we can look at how transfer function can help us to predict changes in the output if the input is subjected to a step change. For example, we want to determine the response y of t to a step change in x with magnitude m at t equals to 0 using a transfer function we determined before. So step change in y, meaning we'll have a magnitude of m. Initially it's the deviation is 0, then suddenly the deviation comes. That is a step change. And we want to first find big Y of S. Because the definition of the transfer function is the output divided by the input in the Laplace space. We choose to use deviation variables. We want to rearrange big Y of S. So it is G of S multiplied by X of S. And G of S we know, but X of S we don't know, but we can get from X prime of T. X prime of T was defined as magnitude M constant, so that we can take the Laplace transform X prime of T. That gives us the big X prime of S. And the Laplace transform of a constant is constant times 1 over S. And now we have G of S, we have X prime of S, we can substitute in. So big Y prime equals 1 divided by S plus 1 multiplied by M divided by S. And now we want to get the deviation in the time space. Then we'll do the inverse Laplace transform for big Y of S. That will give us small prime Y prime of T. To do that, we need to form the inverse Laplace transform for M divided by S plus 1 times S. And we want to carefully identify from the Laplace transform table, then we can use for this expression. And I found that the inverse Laplace transform of 1 over S plus B1 multiplied by S plus B2 equal to 1 over B1 minus B2 multiplied by e to the negative B2 t minus e to the negative B1. Okay, so let's apply it to here. What we have. So the M at the top is a constant. We can take it out of the Laplace transform, inverse Laplace. And S plus 1 gives that B1 equals to 1 and B2 equals to 0. Now we can substitute B1 and B2 inside. So 1 over 1 minus 0, this is just 1, e to the negative 0 of t minus b e to the. We can simplify this. We have m e to the 0 is 1 minus e to the negative 1. Okay. But remember, this expression is y prime of t, but we want to find y of t. And y of t, recall that y prime of t is equal to y of t minus steady state. So y of t equals to y prime of t plus the nominal steady state value. Although we're not given one, we can just write the value out. It's m times 1 minus e to the t plus the original nominal state. This is our final answer for the response. So now we have experience obtaining transfer functions and using transfer functions to predict changes in output when we have changes in input in simple system. Now we want to apply it to a more complex system and using different weird variables. So let's look at a book example. Find the transfer function model between the liquid level H and the inlet flow Q of I in deviation variables using the governor equation provided. First, let's identify the ordinary differential equation, which is already derived. We don't have to do that. And what is the input? And what is the output? The input is Q of I. And this is the cause. The change in inlet flow rate will cause change in the liquid height, and therefore the output is H. And then we also identify constant of A and R of V. Okay. So first, we want to find the steady state expression, steady state ODE. So steady state means that dt is 0, and everything is at nominal steady state value. 0 equals to Q of I minus 1 over RV H. All inputs and outputs are at steady state, so give them a bar. And then we derive the ODE in deviation variable by subtracting the original ODE with the steady state value. So we have the deviation as A dH dt equals to Q of I minus Q I bar minus 1 over RV H minus H. As before, we can use the definition of deviation variables. Q of I prime minus 1 over constant H. At the left, we still have that dH term, and we can do that as before, dH prime dt, using the definition of H prime, which is H of t minus nominal steady state, equals to dH dt, because the derivative of constant is 0. So since they are equal, then we have a dH prime dt. Now we have derived these deviation variable ODE. We keep looking at them and say they're similar, but we do need these derivation steps, as we will see in future. If we hold one thing constant, then it will go out, so they will not be the same. After we have derived the deviation variable ODE, we can now find the transfer function, taking the Laplace transform of the deviation ODE both sides. On the left, I have A times H prime of S minus the initial value. Notice that the initial condition, H prime of 0, is H of 0 minus the nominal state. Normally, H of 0 is at the nominal steady state, so H prime of 0 is 0. That is why we use deviation variable. That on the right side, we have big Q of I minus a times big H. We can rearrange A S H plus constant equals to Q. And we can isolate H prime of S equals to Q of I divided by A S plus 1 over R. To make it cleaner, we can multiply by 1 by multiply top and bottom R of V. Q of I R of V divided by A R of V plus, and H of S is the output, Q of I is the input. We can divide it by both sides. So we have out divided by in, and that is the transfer. For doing that, we have R of V divided by A R of vs plus. Usually we can write it in a standard form where it's k divided by LLS plus 1. We'll see in the future why that is. Here we have k is defined as RV, tau is a, and we have found the transfer function for this more complicated model. And why do we want to find that transfer function? It is because we want to model, predict any output changes if we have any input change. Here we want to determine the response of h of t, output, to a step change in q, which is the input, of magnitude m at t equals to 0 using the transfer function we just determined. So again, we want to rearrange for the output deviation in the Laplace space equals to p of s, qi of s. Q of s we know, but we don't know qi of s. But we do know that it is a step change, magnitude m, constant. So if we take the Laplace transform of that, it becomes uppercase. Oops. To be in the S domain or the Laplace domain. The Laplace transform of constant is constant divided by S. We now have Q. We have R V A R V S plus 1 times M. Okay. Now we want to get the deviation response in time space, which is H prime of t. Do that, we do the inverse Laplace transform H prime of S, which is the inverse Laplace transform. That whole thing. Again, we want to carefully look at the Laplace table and find the thing that we want to use. Found that the inverse Laplace transform for S plus 1 B2, 1 over that, equals to 1 over B1 minus B2 e to the negative B2t minus e to the negative B1t. In our case, we have R and V, R, V, and M are constants taking out. I just want to rewrite this a little bit so that we have inverse Laplace of RVM divided by, we want to isolate the S term, divided by A RV for both top and bottom. At the bottom we divided by ARV, then 1 divided by V, and the top as divided. So that the constant becomes divided by ARV, RV cancels out. The Laplace transform we identify B1 equals to 1 over ARV and B2 equals to 0. We have B1 minus B2, 1 over RV minus e to the negative 0 minus e to the negative 1 over ARVT. And we simplify, gives us a RV 1 minus e to the negative t divided by a. Oh, and not to forget the constants front, which is m divided by a. We can further simplify. We have m RV 1 minus e negative t divided by a. Is that it? No, because we only determined t prime of t in the deviation space. What we do want is in the time space h of t, which is the deviation plus the nominal steady h can write. But we are not supplied with h bar, so we'll just write it out. Minus. That is our final response. So in this video, we defined the transfer function. We covered how to obtain the transfer function from ordinary differential equations, whether it's from the original space or the deviation space. And we finally looked at how we can use transfer function to predict output changes if we have a step input change.